Hi, I'm Arthur Wang. This is my Lab 30 Black Hole lab report. For the lab instructions, we're told a star is orbiting a black hole of unknown mass located at the origin. We will then analyze the star's motion to find the net force on the star for all points in the dataset using the scaffolded starter code beginning on line 96. Assume the net force on the star is due solely to a black hole located at the origin and that the time between data points in your trajectory is 1 day. This is part 1. For part 2, your mission is to fly around the black hole, not necessarily orbiting it, but rather getting close to it at some point without crashing on the planet or the black hole. To do this, you'll need to determine what initial velocity your ship must have when it leaves the surface of the planet. So here are some relevant equations. So first we have the velocity update and then the position update. Both of these are derived from Newton's second law. And then we have the gravitational force equation. So F net grav equals negative g m1 mass 2 divided by radius squared times r hat, where r hat designates the direction. So for part 1 code, we have the mass constant we were given in the instructions. We had to find the time in 1 day, also given in the instructions. So this is the amount of seconds in a day. Then we have this other starter code. And over here, we have the momentum vectors, which is calculated in the form P equals mv. So we find that for both initial and final. And then here, we find the change, v final minus v initial, p final minus p initial, and then dp dt, so change in p over change in t, so that's here. And then f net equals dp dt. This is a mathematical identity, I guess. These are equal. We infer that. And then we also have to calculate the parallel and the perpendicular components of the momentum. So that's done here, and the f net will just be identical to each of those elements of the momentum. So here we rearrange the equation on the last slide, in which we have f net, find the f net grav, but in this case we are just trying to find it so that we can find the second mass, so we can find the mass of the black hole. So this is just the previous equation rearranged to solve for the mass of the black hole. So this is what the graph looks like for the code for part 1. It traveled on this trajectory and went around, and yeah. For part 2, we have the initial conditions, and then here's my speed that I was able to find, so that the ship would not hit both either the planet nor the black hole itself. And over here we have the calculation loop. This is where we find the different forces relative between each of the different, I guess, objects that we have in the system, as well as the different positions that we have between the different objects in the system, which will affect the force. And here is another application of the Newton's position and velocity updates, so between the different elements of the system. Alright, so this is my graph. The planet was all the way on the side. I suspect it was due to unfortunate seeding, but I had to get it to curve all the way around the planet, so this is heavily zoomed in. But yeah, the spaceship curves around the black hole, which is right here. Alright, so for the what if questions, we have what does it mean? In your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. Okay, so in regards to this lab, net force is mathematically equivalent to rate of change of momentum, meaning there's no difference between them mathematically, except dp dt, or our momentum, or rate of change of momentum, is measured. So we calculated it, and then all of the elements of f net are just inferred from the measurement of dp dt. So f net is equal to, but it's just inferred. Okay, so for part 2, what if we are trying to enter an orbit around the black hole rather than just going right next to it? So what kind of initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Your spaceship should still not crash into the black hole nor crash into the planet. So if we wanted the ship to orbit the black hole, we'd increase the y speed and lower the x speed. Because at least in my model, because the planet is super close to the ship at the very start, we have to bypass the planet with these elements to then arch all the way over to the black hole. Thank you.